A quantum number tree is just a way of displaying all of the possible quantum numbers associated with typically a principal quantum number, like n equals 3 level, just to show how many different electrons should be able to fit into orbitals of that size. The idea here is that we're going to make a tree where we start with just one possibility, and then we split based on the number of possibilities available at each subsequent level. So let's say, for example, if I start with the n equals 2 level, then I consider my restriction on L, which is that L can go from 0 to n minus 1. If I have 2 there, then I can see that L can be 0 or 1. So I split at this level to two branches. One branch represents the L equals 0 level. The other branch represents the L equals 1 level. And then I do the same thing for orientation. For the ML, for the L, the only orientation I have is 0. Remember, my restriction for ML is that it goes from negative L through 0 to positive L. So if I only have one possible here, then I would just go straight on to my ML equals 0 case. On the other hand, for the L equals 1, my ML value could take on three values, negative 1, 0, and 1. So then I break off into three branches here, negative 1, 0, and 1. And then finally, regardless of the previous things, my MS can always have a plus or minus 1/2 value. So all of these branches break into two branches, all representing plus 1/2 and minus 1/2. And I could write this on all of them, but I'll just do it for a couple so you get the idea. And so what this illustrates then is that at the n equals 2 quantum level, I have 1, 2, 3, 4, 5, 6, 7, 8 possible locations for electrons, or electrons that can fit. I actually have 4 possible locations, but then you double the number of electrons in each location, so I have 8. This n equals 2 shell has a capacity to hold 8 electrons. If I want to just look at part of the tree, for example, I can see here that what this tells me is that the L equals 1 has a capacity for 1, 2, 3, 4, 5, 6 electrons. So a quantum tree is just a nice way of representing how many electrons can fit within a given condition. Let's go and do the big one then. Let's do the n equals 3 tree. You can do an n equals 4 tree too, but it's just getting to be quite a bit of work, so I'm only ever going to do a 3, and just because I don't want to do the whole thing. So for the n equals 4 level, I'll start with that. And then I have the possibilities for L. So L can go from 0, 1, 2, but I don't want to do n equals 4, sorry, I wanted to do n equals 3. 0, 1, and 2. Then so I can split up into those. I won't do an n equals 4 because it's just going to get too big and messy. And n equals 3 is plenty. You're going to see it's going to get messy enough. So for the three possibilities, I have L equals 0, L equals 1, L equals 2. And then my ML values, for L equals 0, it can just have 1, which is 0. So just one branch up here. For my L equals 1, ML can have three values, negative 1, 0, and 1. So that can break up into three branches, negative 1, 0, and 1. And for my L equals 2, my ML can break up into five values, negative 2, negative 1, 0, 1, 2, 2, 3, 4, 5, 2, negative 1, 0, 1, and 2. And then finally, for my MS level, I just split all of these into their plus and minus 1/2s. 1/2, minus 1/2, 1/2, minus 1/2, 1/2, minus 1/2, 1/2, minus 1/2. I'm just not going to bother writing it out. It's already getting messy enough. And so what this tree illustrates is that an n equals 3 is comprised of 2 0 electrons, 1, 2, 6 L equals 1 electrons, 1, 2, 3, 4, 5, 6 electrons, and 10 L equals 2 electrons, 1, 2, 3, 4, 5, 6, 9, 10, for a total of 2, 6, 10, a capacity of 18 electrons. So the size 3 for electron orbits can actually contain 18 electrons. So that's how you can use a quantum tree, number tree, to show how many different electrons or how many different orbits there are for each condition, and then how many electrons can go into those orbits.